Hey guys, welcome back. We are on this counting permutations and combinations assignment that we did in class on day 3. In the previous videos we did page 1 talking about the fundamental counting principle and some examples. In the video 2 we talked about factorials, and now we're talking about permutations. Okay, so the definition of permutation is an arrangement of objects. Those could be numbers, letters, people, whatever. The important thing here is that order matters. Okay, so in this first example, imagine you have 5 posters you want to hang on the wall of your bedroom. How many different ways are there to order your posters, assuming they're going to hang side by side? So this is actually going to go back to the fundamental counting principle. We're gonna treat choosing a poster as an event. So what I'm going to do is I'm going to list out 5 spaces. These are going to represent my 5 posters, and I'm just going to choose them in order. Okay, so for the first poster, the farthest left poster, I'm going to have 5 choices because there's 5 posters. But as soon as I pick that first poster, I can't choose it again because all these posters are different posters. So the first one is now set in stone, and I only have 4 possible options. Okay, now I choose the second one from those 4 and put it up. And now for the third one, there's only 3 possible options. And I choose from those 3 options. And then I have 2 more options after that, and then 1. Okay, so altogether that's going to be 120 ways to hang these posters up, 120 different possibilities. So each poster, choosing each poster, is basically an event, but the number of possible ways to do that goes down each time as I go through and get rid of some of the posters by hanging them up. But notice that this is actually 5 factorial. So the whole reason we talked about factorials above here is because we use them when we're doing the fundamental counting principle. We use them for like counting number of possibilities. So there's got to be a better way to represent this, right? There is. It's factorial. So if you have n objects, the number of ways you can arrange those objects is n factorial. If I had 10 students, for example, and I wanted to put them in a line, there are 10 factorial ways to do that. For the first student in position 1, there's 10 possibilities. But as soon as I choose student 1, there's only 9 possibilities for the next person, and then 8 and 7 and 6 and so on. So that's kind of interesting. Factorials we use when we're trying to determine number of possibilities. This next example is slightly different. You'll see why in a second. In this example, we have 5 students competing in a science fair, and I named them kind of in alphabetical order to kind of help us list these out a little bit. So Anna, Bob, Chad, Devin, and Esther. A medal will be given out for first and second place. List all the possible outcomes for choosing first and second place winners from 5 contestants. So we got these 5 people, and we're going to choose a first and second place. So I'm going to use an A for Anna, a B for Bob, a C for Chad, a D for Devin, and an E for Esther. And I'm just going to start arranging these kind of in alphabetical order, or just like kind of systematically so I don't lose any. So let's start with Anna in first place, and then Bob in second place. That's a possibility. But I could also have Anna in first place and Chad in second place. Or I could have Anna in first place and Devin in second place. So notice I'm just matching people with Anna, right? That's kind of alphabetical order if you think about it. Okay, I could have Anna and Esther. So the ordering represents first place, second place, first place, second place, first place, second place, first place, second place. So those are all the possibilities where Anna is getting first place. All right, now we can also kind of like rearrange these. So if you think about flipping the order, if I had B then A, that would represent Bob getting first and Anna getting second. And so these are actually 2 different options, even though they look kind of similar. Similarly, we could have Chad in first and Anna in second. And we could have Devin in first and Anna in second. Or we could have Esther in first and Anna in second. So those represent all the possible outcomes where Anna is getting first or Anna is getting second. Now we've got all the Annas out of the way. We don't have to worry about pairing Anna with anybody anymore. Now we're going to do all the Bob combinations. Okay, and it looks like there's going to be a lot, but actually this is going to get less and less as we go because we've already paired Bob a couple different times. So the next option here is I could have Bob in first and Chad in second, right? So Bob Chad, then I'm going to go Bob Devin, then Bob Esther. So all the possibilities were Bob's in first. So Bob wins, Chad second, Bob in first, Devin in second, Bob in first, Esther in second. Okay, now let's do the possibilities where Bob's in second place. Well, Chad can be in first and Bob can be in second, or Devin can be in first and Bob can be in second, or Esther can be in first and Bob can be in second. Notice we already have Bob and Anna and Bob, so we don't have to worry about those ones. Okay, so now we've exhausted all the possibilities with Bob in first or Bob in second. Okay, now we got Chad and Devin and Esther. So we could have Chad in first and Devin in second, or we could have Chad in first and Esther in second. Those are all the possibilities where Chad's in first place. What about a Chad in second place? Well, you could have Devin and Chad, or you could have Esther and Chad. Notice that we already have the other possibilities. We've already have all the ones with Bob and Anna, so we don't have to worry about those. We've already paired Chad with Bob and Anna. Okay, so we're done there. Okay, now we can have Devin and Esther, or Esther and Devin, and those are our last two. So Devin and Esther, or Esther and Devin. Okay, so kind of systematically or kind of alphabetically, we're going through all the possibilities here. So it looks like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 different ways for that to happen, and we've listed them all. All right, now we don't always want to list them all out. This is kind of an exercise to help us understand what's happening, but we're actually going to kind of do the same idea, the same problem again, in maybe an easier way. Okay, so this is all the different outcomes. Okay, the next part says use the fundamental counting principle to determine number of possible outcomes for choosing first and second place from 5 contestants. So it's the same scenario, but instead of saying list them all, it's just saying how many are there. Well, the fundamental counting principle would say choosing first place is an event and choosing second place is an event. So if you think about what's happening here, when you choose a first place, you have 5 contestants to choose from. You can choose Anna, Bob, Chad, Devin, or Esther. But as soon as you choose a first place, you can't choose that same person for second place. And so you have a different number of options. You have 4 options after that. So notice it kind of looks like a factorial. The difference here, though, is we don't have the 3 times 2 times 1 because we're not choosing a third place, we're not choosing a fourth place, we're not choosing a fifth place. We're just saying we got first and second and that's it. We don't care about the rest of them. We're not placing them. So this is going to be 20 outcomes. 5 times 4 is 20. That matches what we got here, right? Here we saw all 20. We listed all 20 out. We saw there was 20. Here we use the fundamental counting principle. The question is, how can we express this idea that you want a factorial, like count down from 5, but stop after you've gotten 2 options or 2 different choices? If you go back and you think about the permutations that we did before, or the factorials that we did before, something like this, 7 factorial, 3 factorial. Remember that this was just 7 times 6 times 5 times 4. We just stopped at 4. If you write that all the way out, you'll see why. Remember that these canceled. So one way to say, hey, count down from 7, but don't give me anything 3 and below, just stop at 4, is to say, okay, get rid of everything 3 and below. We just do it with a fraction, okay? So going back to this idea, how do we represent 5 times 4? Well, I'm just going to go one step back. It would be 5 factorial, and we want to stop as soon as we get past 4. So that would be 5 factorial over 3 factorial. Right? That's how we would represent 5 times 4. Another way to think of it is this is how many people you have to choose from, and this is how many people you're not going to be choosing. I chose 2 people, which means there's 3 people I'm not going to be choosing. That's one way to think of it. So in general, this is how you do a permutation of n objects taken r at a time. The notation looks like this. You have an n, and then you have a big P, and then you have your r. N and r just represent numbers. What you do with those numbers is you take n factorial and you put that on top, and then on the bottom you put n minus r and you do that factorial. Okay, this is the total number of options, and this is the number of people you're not choosing, or this is basically where you want to cut off your factorial. So going back to our example here with our 5 contestants in our first, second, third place, or first and second place, this would be 5P2 because there's 5 people you're choosing from, 5 objects you could say, and you're going to take them 2 at a time. You're going to choose 2 and the order is important. So I would say that this is 5 factorial over 5 minus 2 factorial. Right? You simplify 5 factorial over 3 factorial. Right? 5 minus 2 is 3. And you're like, oh, okay, that's 5 times 4, right? Because you do 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. But remember, the 3, 2, 1 are going to cancel, and we're just going to have that 5 over 4, which we know is 20. So this is the formula and the notation that we use in a situation where we're doing permutations. When we're choosing less things than we have to choose from, and the order is important. All right. So a museum wants to display 3 paintings side by side on the home page of their website. They have 12 to choose from. How many ways do they display the 3 paintings? Well, there's a couple ways to think about this. Okay? The first is just think about the fundamental counting principle, which is kind of where everything starts. Fundamental counting principle says you got 3 choices because you're going to choose 3 paintings. You have 12 to choose from, so you're going to start with all 12 to choose from, but as soon as you pick that first one, you can't choose it again. You got 11 left to choose from. And then as soon as you pick that second one, you only have 10 choices to choose from. So you can use the fundamental counting principle, and this is just 12 times 11 times 10. Since 12 times 11 is 132, then 132 times 10 is 1,320. That's how many different ways there are to arrange those pictures. Now from a different perspective, using the formula, you could say, well, this is 12P3. I have 12 paintings. I'm going to choose 3 at a time, and I'm going to see there's different ways to order those. The order is important. All right, so that would be 12 factorial over 12 minus 3 factorial. In other words, I'm going to have 12 factorial. I'm going to choose 3 paintings, which means I'm not going to choose 9 of them. So this is kind of like dividing out the ones I'm not going to choose. All right, well, that's 12 times 10 times 11 times 9 factorial over 9 factorial. Well, the 9 factorial and the 9 factorial cancel, and there's my oh, sorry, I wrote this in the wrong order. This should be 12 times 11 times 10. Sorry about that. Same thing, but it should be in order. 12 times 11 times 10, which again is 1,320. So really, this notation here is just a symbolic way of representing this pattern, of saying, okay, you got 12 things, you got to start counting down from 12, but stop when you've made your 3 choices. Well, to stop from a factorial, you have to cancel out the rest of it, and so you have to have a division kind of idea. You have to have a fraction where you're dividing out the other 9 factorial orderings that I don't need. So hopefully that kind of connects those 2 ideas. All right, now down here, this is just notation practice for you. So there's 4 of these. Now, I think when I originally printed this out, well, I put a 98 here, but that actually doesn't work out so well. So what I'm going to do is I'm going to change this to a 2. So this is 100 P2. So if you get A-Day, guys, I was working at the kink still, had a couple errors. So B-Day, you're in good shape because I caught all those. But you're just going to do these 4. So let's do this number 4 together just so we have it, and that'll be a good example. So 100 P2 is kind of like you have 100 things to choose from, but you're not going to choose 98 of them. Okay, so I need to choose 2 things of 100, so I got to cut off my list. I got to go 100 and then 99, and then that's it. All right, so this is 100 factorial over 98 factorial. Okay, but again, and that looks kind of scary, but we've done this one before. This is 100 times 99, and then I'm going to do the rest of them and the rest. All right, and there's the rest, 98 factorial. So these cancel. I just have 100 times 99, which is 9,900, or 9,900. Okay, so that's how the formula works. But remember, the formula is just trying to get you to think about the fundamental counting principle. So another way to do it is say, okay, I got 100 objects to choose from. I'm going to choose 2 of them. There's 100 choices for the first one. There's 99 for the second one. Right? So either way. The notation is important. The formula, knowing how the formula works and knowing what it means is important. But again, the formula, this guy, it just represents the fundamental counting principle, counting down but stopping at a certain point. All right, in the next video we'll talk about combinations and compare those to permutations. So tune back in just a minute and we'll get the rest of this. Thanks.